Hello everyone, myself Manisha Sawant. I am from Vidyadeep Institute of Engineering and Technology. In last lecture, we study function. We studied function of complex variable and some basic definitions of complex functions. Okay, in this lecture, we are going to learn and see some examples by using basic definition. Our first example is sketch the following sets and determine which are domains. First is I am of z is greater than 1. Second one is 0 less or equal to argument of z less or equal to pi by 4. Third one is modulus z less or equal to 1. Okay, we know that the Cartesian form of complex number is z is equal to x plus iy. We are using here the Cartesian form of complex number z is equal to x plus iy. Now our first case, im of z is greater than 1. It means im of z means imaginary part of z. Okay, imaginary part of z is y. Y is greater than 1. Okay, for this first we have to sketch diagram, then we can see in this graph we can see we sketch diagram for y is equal to 1. This line is for y is equal to 1, and here we have condition for y is greater than 1. It means the points are greater than 1 means these points. Okay, we can clearly see that so all points are greater than 1 is open set. Okay, here all points are open, there are not any boundary there, so yes, it is domain. For domain we have two condition. It is connected. First condition is it is connected and second is open. Okay, it is open and connected both. So we can see first case means im of z is domain. Now second is 0 less or equal to argument of z is less or equal to pi by 4. Okay, argument of z means theta, and the value of theta is tan inverse of y by x. Therefore we can write 0 less or equal to tan inverse y by x less or equal to pi by 4. Okay, then we take multiply tan with this inequality, then we take we get tan 0 less or equal to y by x less or equal to tan pi by 4. Okay, the value of tan 0 is 0, value of tan pi by 4 is 1. That's what the next step is 0 less or equal to y by x less or equal to 1. Okay, for this condition we sketch graph here. Okay, you have given angle pi by 4. So if from the graph we can see the set is open. Therefore the condition of domain is fulfilled here. Therefore we can say yes, it is domain. Okay, now third one. In third one, modulus z is less or equal to 1. Okay, z is our x plus iy. Okay, therefore we can write modulus z x plus iy is less or equal to 1. We take square both the side, then we get modulus x plus iy all square is less and less or equal to 1. square. 1 square is 1. Therefore we can write modulus x plus iy square is less or equal to 1. Okay, then we have formula for modulus z is equal to under root x square plus y square. Okay, modulus x square plus y square, but here modulus square, therefore we can write x square plus y square is less or equal to 1, which represent, okay, for this we sketch diagram, means graph. From the graph we can clearly see that the sketch for the given equation is equation of, and it is interior part of circle. Okay, in last lecture we are already discussed about the basic definitions and the interior part of circle. The definition of in interior part of circle we can see x square plus y square is less or equal to 1, means interior part of circle. Okay, which represent the interior of the circle, which it's with its center 0 0 and radius of 1. Since the region modulus z is less or equal to 1 represent the boundary and the interior of the circle. Okay, it is closed, hence the given region is not a domain. Next is limit of a function. Okay, like other function, the complex function has also its limit. Then we see what is its limits. Okay, the definition of limit of complex function is a function f of z is said to have a limit L if for each positive number epsilon there is positive number del such that is modulus f of z minus L is less than epsilon whenever 0 less than modulus z minus z0 less than del. Okay, if function has limit, then the point z has also limit. Okay, if function has limit of limit is less than epsilon, the compulsory the complex number has also limit which is also less than del. Okay, symbolically we can write it as limit z minus z0 f of z is equal to L. Example, using the definition of limit show that if f of z is equal to iz in the open disk modulus z is less or equal to 1, then limit z tends to 1 f of z is equal to I. Okay, we have to prove limit z tends to 1 f of z is equal to I. Solution for this, f of z is equal to iz, we have already given z0 is equal to z1 and w0 is equal to L. Okay, let this is by using definition we can write modulus f of z minus wz is less than epsilon where epsilon is greater than 0. We put the value of f of z and wz, which is value of wz is I. Wait, place one correction here. W0 is equal to I. Okay, we can write modulus iz minus I is less than epsilon. So we take common. We take common as a we take I as a common. Then we get modulus I into modulus z minus 1 less than epsilon. Okay, modulus z value of modulus I is equal to 1. Therefore modulus z minus 1 is less than epsilon. Okay, this condition is satisfied by the points in the open disk modulus z less or equal to 1. Assuming epsilon greater equal to del, the following conclusion can be made: for every epsilon greater than 0, there exists del greater than 0 such that modulus f of z minus I is less than epsilon. We just consider epsilon is equal to del and we put the value epsilon is equal to del in the definition of limits. Okay. Okay. Whenever modulus z minus 1 is less than del, hence limit of z tends to 1, f of z is equal to I. Okay, we are just using the definition of limit for the evaluate the limit. Okay, we stop here. Here in next lecture we are discussing about continuity or in complex function. Thank you.